No. Okay. I think this one should be okay for you as well if you've seen this stuff before. Let's have a look. Okay. So if we can write that down now, we're going to have a look at velocity time graphs. There's two science students that want to study financial maths next year. I think they should be in the physics class instead of the biology class. So I've asked Connell what he thinks about this. So we might get two more students from science. I think you probably agree, if you want to study maths next year, you should study physics instead of biology.
Yeah.
I think it's a smarter choice. Okay. Velocity time graphs. Does anybody know this name? Have you seen these before? Yeah? Let's have a look. Okay. So just before we start, we have something here called a sign convention. Does anyone know the meaning of this word, sign convention? It's like a sign choice, sign rules. What I mean is, in one dimension we say a positive means to the right, and a negative then would mean to the left. Now, the reason this is called a convention is not like a rule, okay? In fact, if you wanted to, you could say left is positive and right is negative. It's fine. But it's usual to say right is positive and negative is for left. So we call it a convention, a guideline. And vertically, up is positive and down is negative. Okay? But, of course, you know this already, but the point I really want to make is, this is what we usually do. But for some questions, sometimes it's actually convenient to call maybe this positive and this negative. But we usually do this. This is what we usually do. But I think you knew that, so that there might not be nothing. You might not need to write anything here. But if we think about it, this means that a number could technically be a vector. Because what do we need for a vector? We need a size and a direction. So if I have the number -2 meters per second or +2 meters per second, these are actually vectors. Because you have a size, a magnitude, but you also have a direction. What's the direction here? Yeah, the sign is the direction here. So, therefore, a single number could actually be a vector. That's the key here. For example, s equals 1 meter could mean 1 meter to the right, and then s equals -1 meter means 1 meter to the left. I think you're okay with this, yeah? Oops. Okay, so now on to some definitions. Acceleration is what's coming up. Does anybody know or remember the definition of acceleration? What do we think? You remember?
Increase of speed over time.
Yes. One word needs to be fixed in that. Sorry, two words need to be fixed in that. You fixed one of them. There's another one. You said increase in velocity over time.
Increase or decrease?
Yeah. So change, yeah. Change in velocity over time. So let's have a look at the formal definition. Acceleration is a vector. And it's the change of velocity per time. As a formula, we can write it like this. The change in the velocity over the change in the time. You should write all of this definition down, please, for sure. Okay. Let's see now. Where delta v is the change in velocity and delta t is the time. By the way, what's the units for acceleration? I didn't write them down, but what's the units here? Yeah, you have meters per second over per second, so it's... No, sorry. Meters per second over seconds. So that's meters per second squared then. Okay. Somebody, if I remember, studied an American syllabus for physics. That was you, yes. So you might use different letters here, VF and VI. Yes. So here we use the letters U, V, A, T, and S to represent different parts of motion. So we use the letter U to represent, well, you could probably guess, but maybe they might know if they've done this before, or maybe you might know. What's the U represent? Yeah, the initial velocity, the velocity at the beginning, which is called the initial velocity. The V, yeah. You would have called this VI and VF. Yeah, and final velocity, yeah. The A, obviously acceleration. The T, time. And lastly, the S, displacement, which is often also distance as well. Okay, did you write down what you needed to? Yeah? Continue? Yeah. Okay. So here's an example here. What would be the U for this event? 0. Well, the U is the starting speed, so everybody starts for this race at 0. Yeah. Okay, this maybe is a harder one, but roughly, what do you think the V might be here at the end? You have to have a guess. 9.8. No. What do you think the V is?
0.
No. Does he look like a 0 now? Going at the end. No, it'd be quite fast, I would have thought, at the end of the race. What's the V? No, just have a guess. Like, what do you think? How many meters per second? Yeah, but maybe a bit faster than 10. Why am I saying a bit faster than 10? Well, because what's the T for this race? Oh, come on, don't you? You know this guy, the fastest man in the world.
Yeah, but I don't. So long. Yeah.
Roughly, what's the T? Roughly.
10.
Yeah, it's about 10 seconds. It's less than 10 seconds, but it's about 10 seconds. And what's the S? 100 meters, good. And the V is actually about 14 meters per second. Yeah. The reason it's more than 10 meters per second is because he started at rest. He didn't start at 10 meters per second, so he must be going faster than 10 at the end because he has to make up nearly for the slower start, you know. So actually, at the end of the race, Usain Bolt is running at about 14 meters per second. Now you need to picture that. 14 meters, that's pretty far, right? 1 second. Pretty fast, right? So this is an example of how you could use UVATS then. And I'll just remember, I want to remind you that velocity can be positive or negative because it's a vector. But speed is only positive. And also, displacement can be positive or negative because it's a position. But Distance can only be positive. Okay, so please remember that, please. Do not confuse speed and velocity or distance and displacement. Okay, got that? Warning message? Yep. So even though I tell you this, some people will sometimes forget this. So try not to, okay? Right. Usually, it is true, usually they're the same though in most questions. Velocity and speed, distance and displacement. But they're not always, so you've been warned. Okay. Often it's quite convenient to represent the motion as a velocity time graph. So all a velocity time graph is, on the x-axis is the time in seconds, and on the y-axis is the velocity in meters per second. So let's have a look here. We imagine this as a story. Before you draw this, let's just have a look at the story here. Okay, so you could picture if I was in my car. What does this tell me at the start if I was in my car? Well, the car begins at rest. Okay. And then, how would you describe this motion?
Acceleration.
Yeah, but like describe it more. Like what type of acceleration?
Constant speed.
Yeah, but not just simply. Simply, what am I doing in the car?
Speeding up.
Yeah, a lot or a little? A little. So in other words, I'm moving off slowly to begin with. Yeah. And then what would you say happens here at this point? Like if you were to describe what I was doing in the car, what have I done here?
Pushed again.
Yeah, I put my foot down more and I accelerate faster. Now what happens here, do you think? Yeah, so maybe, why am I doing this? What might have happened?
You reach the...
No, I don't think traffic, yeah.
You reach the limit speed.
The speed limits, yeah. So maybe this is me driving out of the house, and then this is me driving on the motorway, the highway, and then this is me at the speed limit. What happens here? To here?
You're coming to a stop.
Yeah, but more details, like something very dramatic is happening.
Pushing the brake and then...
I don't think I would brake this hard if it's not like, oh, I'm here. What would you think has happened here? Maybe there was an accident up ahead and I had to slow down very quickly, So, rapid deceleration slows down here. Okay, what's happened here now? Stopped because, I don't know. Maybe I hit a student and I have to brake suddenly and then I stop here. Something like this. And then what happens here?
You pull back.
Yeah, so I realised I didn't finish the job. The student's still alive. So I have to reverse and then travel backwards at a constant speed. Now, if you've ever reversed in a car, you know that there's a limit to how fast you can go backwards. You can't go as fast backwards as you can forwards. So that's why this isn't a speed limit, this is a limit perhaps of the car. What's nice about the velocity time graph is you kind of get a picture of the whole story, the whole image here. Also what's important with this picture is all these words, these useful descriptions. Accelerate slowly, accelerate quickly, steady speed, rapid deceleration, steady speed in opposite direction. There's nice description words here. And what's another word for steady speed? Constant speed. Another word for constant speed. Uniform speed. Anything else? No, I think that's the main one. can you draw this in your notebook? And it would be great if you could have some of these descriptions as well.
Will there be a vertical line? Like vertical? Yeah.
Technically, you cannot quite get exactly vertical, although in some of the graphs you can consider it perfectly vertical, but it's technically not possible because that would mean you instantly stopped, which can't really instantly stop, you know. Like even if the car hits a wall, it doesn't instantly stop, it still slows down as it's colliding with the wall, you know. You drew this? Oh, draw it for me. Draw a nice, beautiful time, velocity time graph. Oh. It's alright. You drew it? Yeah. Yeah. You're drawing? Okay. What's your timetable like today? Do you have a class at 9? Oh, it's your first class then. And then after this class? Okay, that's not so bad. And then?
AP writing.
3 hours? And then finished?
Individual tutorials.
Okay. Who is your tutor actually? Conno? Lorraine? For the individual tutor, okay, yeah. Alright, continue. Do you have that? Yep. Alright. Okay, so here's a small question for us to do it together. A car starts from rest. It slowly accelerates to 20 meters per second over 10 seconds. It then maintains its speed for 5 seconds before suddenly decelerating to rest over a time of 4 seconds. Draw the graph for this. Okay, so I don't think this is too hard. I'd like you to draw this for me now, and then I'll do it on the board. So if you can draw this graph neatly. Okay, you've drawn it? Yeah. Let's have a look. Good, yeah. Yeah, very good. It looks like you all have the right idea. Can I see? Good, yeah. Good, good. And how about at the end there? Can I see what you drew? Or you're not finished yet? Looks okay. Can I see? Yeah. Everybody has the right idea. Very good. Okay, so I don't need to draw this on the board because everybody got it right. Good job. Okay. You might remember this triangle from middle school. We call it Dad's silly triangle here, or distance, speed, time. And I think you all know how this triangle works. It's very sort of a basic idea. You have a relationship between distance, speed and time, which you can nicely draw on a triangle here. Distance, speed, time. So it means if you want the distance, that's equal to the speed multiplied by the time. If you want the speed, that's equal to the distance divided by the time. And if you want the time, that's equal to the distance divided by the speed. You've seen this triangle before? Yeah. So you all know this basic triangle, and here's it again. Distance is speed multiplied time. Time is distance over speed, and speed is distance over time. So you don't need to draw it 3 times. If you can just draw it once. Although this triangle only works in certain situations. It doesn't work for every problem. Does anyone know the requirement for the criteria? Like, when can you use this triangle?
We have 2 of them. 2 of them.
True, and something else though. What I mean is something about the motion. Constant what? Oh, you should have gone with what you were about to say. Constant speed. This triangle works when there's no acceleration. So if speed is not changing, you can use this triangle. So this is for no acceleration. But of course, it only works when the velocity is not changing. That is 0 acceleration. Okay, so if you can just draw that triangle, but make note that it's only suitable when there is 0 acceleration. Okay, we got that? Yeah. Now, what do we do if the u changes to v? Well, actually, yeah. What might you do if the velocity does change? If we have a u at the beginning but a v at the end, and we still want to use this triangle, but the velocity is changing. This is actually a common problem in physics. Some of the formulas in physics only work if the thing is constant, but you still need to use the formula and the thing is not constant. So what might you do? So here is a good example. The velocity changes from u to v. You still want to use this triangle. So what do you do? Any ideas? Interesting. Nobody knows? No guesses? Good guess, but not this. Yeah. So your solution was basically to only use the u. Fine. Any other ideas? So he understands, or you all understand, that the problem is you can't use both u and v. You can only use one of them. So your suggestion was to use only the u in the formula here, not this. So what's another suggestion? No ideas. Don't be shy. Go on, somebody must be thinking, maybe use the v. Not this either, if you're thinking that. I'm going to tell you, and you're going to be disappointed, because I think maybe you might think of this. No, last chance, anyone? Okay, so when the velocity changes, and you need it to be constant, and you want to use the formula, what you can use in the formula is not u, not v, but the average of u and v. U plus v over 2. You can actually do this. This is allowed. So here, if the speed changes, instead of using u or v, you can use here u plus v over 2. That's actually fine to do. So you can replace things which should be constant with the average. This is actually okay. It's not okay all of the time, but for these problems it's okay. Did anyone think of that? Or no? You didn't want to say though? See, trust yourself. Okay, let's have a look at an example here. A boy walks 2 kilometers to school every morning, and it takes him 30 minutes to walk this journey. What is his average walking speed, assuming he walks at a constant speed? That is, he does not walk faster or slower. Okay, so this is a question that just needs the triangle here. Can you give me the boy's speed in meters per second? Yeah. So he walks 2 kilometers in 30 minutes. What's his speed? That sounds about right. Yeah, it's what's it about 4,000 over 3,600. So it should be a little bit more than 1. Yeah. Let's have an exact answer here. Well, if you want to do it like this, 2,000 meters divided by 1,800 seconds. 1.11 meters per second is his speed. That's okay? I think that should be okay. Right. The velocity time graph actually tells us a lot. You might think it only tells us the velocity and it only tells us the time. That's true. However, it can tell us much more. Let us see. Okay, so if you might want to write this down. What I'm about to write, it's useful. Okay. So here is the time in seconds, and then actually I can rotate it. Here is the velocity in meters per second. Okay. Let's say it starts here and then finishes here. Okay, so let's see what we can find from this. Here, you actually, if you think about the UVATS, you actually know what this part is. Which is this, the UVATS? Which letter is this? This is the T. So by looking here, you can get the T. Oh, that's good, okay. And actually, when you think about it, you know what this is. If you look here, what does this give you? It gives you the U, so that's good. So this gives us the U. And then if you look here, this gives us the V. Okay, well that's good. Now in maths class, you've done slope, gradient, haven't you? Yeah. So what is this point here? This is the point 0, U. And what's this point here on the graph? T, V. And have you done the formula for the slope? Something over something. What is it?
Y2 over
Yeah, y2 minus,
y1.
yeah, over x2 minus x1. So in this example, it'd be what? V minus U over T minus 0. In other words, the change in the velocity over the time. What's that though? Yeah, so actually the slope gives us the acceleration. Now, lastly, let's have a look at what the area represents. Now, the way to do that, we'll cheat a little bit. We'll take a shortcut here. What's the units? Let's have a look at what the units represent. So, if I want the area, I need to multiply the bottom by the side here. So, what units do I have here? yeah, seconds. And when I multiply it by the height, I'm multiplying it by something with what units? Meters per second. So what units do I have here for area? It'll be seconds times meters per second, which is actually meters because they cancel. So this area is in units of meters, which means it must represent what? The distance, yeah. So in other words, the area then represents the distance, which most of the time is the S. So there you go. You have everything on the graph. You have the U, the V, the A, the T, and the S. Everything is represented on this graph, which is what makes it such a useful graph. Okay, I'd like you to just add some notes here about this. The UVATS is all represented on this velocity time graph. Okay. We got this? Yeah? So to summarize, U is the initial height, V is the final height, A is the gradient, the slope, T is the length of the base, and S is the area under the curve. Okay, great. Okay, now for this question, we have to be neat when we draw the graph because we're going to use the graph to calculate some things. So shown in the table below is the velocity of a car at different times. So the car begins at rest, then the car accelerates, travels at a constant speed, then decelerates down to 5 meters per second. So what I want us to do is to first plot this, and then once we have the plot, we'll answer some questions. Okay, so if you can draw this now, and then I'll draw it in a moment. Now you don't have to be super neat, but you have to be neat enough.
Is it okay if we have like 1, 2, 3 and the time and the 5, 10?
Absolutely okay, yeah. So I see you have the graph. That's good. That's good. So now, if you have your graph, let's calculate or try and calculate those things there, and then I'll do that too. So the distance. Well, I don't know. Maybe you actually might need me to do this one. Let's do it together. First, I'll make the graph. So we have our time in seconds, and then our velocity in meters per second. How far does the time go? To 10? Okay. Okay, and the velocity starts at 0?
Yes.
And then 20? 5,
10.
10, 15, 20, 20, 20 again?
No.
15,
10.
15, 10,
5,
5, 5, 5. Okay, let's graph this. So, unlike you, I can choose and use this. Right. So this is the velocity time graph. On the x-axis is time in seconds, and on the y-axis is velocity in meters per second. Okay, so I think from looking at your notebooks there, oh come on. I didn't draw the line. But everybody has something that looks like this. So the first thing I want is, actually, can I draw the line? Is it too late? Yeah, but I'm worried this will not fit it. I might have to. Oh no, it's not going to fit it. No, I'm not even. I know it won't. It'll look really bad. Okay, so the first thing is, let's get the distance. So to get the distance, I need to get the area. To get the area, I need to see what shapes I have. So the first shape here is just a big triangle. So let's actually just put this on the calculator as we go along. Okay, so that's a half the base, which is 4, and the height, which is 20. Plus. Okay, what's the next shape here? It's a rectangle. And how big is the base? 1. And the height is 20. Okay, and the next one is a triangle. We'll put a triangle here, can you see?
Yeah.
And then we'll put a fat rectangle underneath it. Okay, so the triangle is a half the base. So the base is from 5 to 8. 3, yeah. And what's the height here? 15, yes. And then lastly, it's the skinny rectangle here at the bottom, which is 5 by, it's actually a square, is it? Yeah, 5 by 5. Yeah. Okay. So, the distance is 107.5 meters, if you can write that down. Got that? Yeah? Okay, so the next thing, I'll let you try it first before I do it. What's the acceleration? So this isn't too bad. The acceleration. Okay. Do we have acceleration? Yeah. What's the unit?
Meter per second.
Yeah. Because what did you divide? What were your two numbers? 20 divided by 4, yeah. Did you get that over here? Yes? No? Yes?
I can also do it.
Yeah. So it's the height here divided by the base here. So that's 20 divided by 4, which is makes the 5 then. And then the deceleration is this part here, slowing down. What's the height? 15 divided by 3, is it? Yeah, so that's 5. Is it minus 5 or 5? Why? Good, because in the question I said, what is the deceleration? So the minus is already on the D. Okay. Yep, happy with that? Okay. Now I want to give you a hard one. Did I give you a hard one to try here? I want to do one more hard one. Let me imagine up a hard one. I'll draw the graph for you. Okay, so this is time in seconds, velocity in meters per second, and we'll have this, whatever it is, accelerate up to maximum and then decelerate back down to rest down. Okay, and I'll say this acceleration is a 2 meters per second squared, and we'll say this one here is a 3 meters per second squared deceleration, so we'll say minus acceleration there. I'll tell you that. I'll also tell you the total time is 20 seconds. And my question is, what is the V, the maximum velocity in this graph? Okay, let's see if you can do this. Getting answers? Not as easy as it looks, perhaps. What answer did you get?
14.
I don't think it's that, although I'm not 100% sure. Try, yeah. What did you get? Okay. Interesting, huh? This is good. It's good to know you don't know everything. It's good. How are we doing over here? Do we think we have an answer? What do you think it is?
So,
I think it is this. Yes. Now, what was your secret?
because it's the same,
Yeah?
the same coin.
Yeah?
So the time for each business,
Yes?
one triangle.
Yes?
So I just divided the time by both sides.
Yeah. I think you have it. Yeah. You got the right answer anyway. Let's have a look. So, don't worry. I don't think it'll be quite as hard as this in the exam. This is just a hard example that I remember given to people before. It's tricky because at the beginning it looks like, it's easy. But then when you start to do it, you realize, it's not as easy as I thought. So the trick for doing this one, firstly, is we should break this up into two pieces. Okay? And we'll call this piece T1 and this one here T2. And you know straight away something about T1 and T2. You know that T1 plus T2 has to equal 20. And we're happy with this, right? But you also know that this height here is V. And you also know that V over T1 should equal 2. Because that's the slope, the acceleration. And you also know that V over T2 should equal 3 for the second half. So when you look at all of these together, you can say, well, I could say T1 equals V over 2 and T2 equals V over 3, and I can take these two and put it into this one at the top. So now I have V over 2 plus V over 3 equals 20. What's that? 5 over 6V, is it? A half. 5 over 6V, is it? Yeah, but how many V's do I have here? A half plus a third is 5 over 6, isn't it? So this is 5 over 6V equals 20. So 5V equals 120. Come in. So, the door's locked. V equals 24 meters per second. Let's see who got. Yes.
I have a surprise for you.
Wow.
Hi.
Hello.
Past students.
Come in.
Come in, yes.
Is that okay?
It is. We just finished the question there, so it's a good moment.
Wow. So, January engineer students. Meet last year's January engineer students. Wow. Two. Wong is studying cybersecurity in Staffordshire now, and Wong is studying pharmaceutical healthcare, the long one. Pharmaceutical healthcare in DIT. Tan is a pharmacy student. She didn't do engineering, but they wanted to come back and see them.
Yes.
I thought it'd be great for them to meet the engineers while they're
Yes,
here.
yes. And you know who else they met on Monday? Yeah, and Faisal was around. Yes, okay.
They were supposed to meet them here today, but they didn't get out of bed.
Right.
Yeah.
Sounds about right.
Yeah. Not much has changed. Will
They
I
don't-
leave you to mingle and chat?
Yes, they can even
Ask them
join the class if they
Brilliant.
want.
Join in.
Nice.
I'll see you back in the office. Yeah?
Okay.
Yeah. Okay.
So, do you have any advice for these students?
Advice.
Yeah, go on, give them advice now.
Bye-bye.
Me?
Yeah, go on.
Bye.
Why don't we
Always listen to Stephen.
No.
Good advice. Good advice. Anything else?
Networking is very hard. And when you not understand, ask people.
Yeah. Ask Stephen when you have a question.
Yeah,
That's
I
also
remember
good advice.
she asked so many questions. She asked me
Really?
in class.
Yeah.
Yeah, go on, you did ask many questions. Yeah. Yeah.
Did I?
I know you did, yeah, you did.
Ladder.
Continue. Anyways, actually guys, you didn't get a chance to ask the students on Monday. I don't know if you had any questions now about anything that you want to ask these students. No, you don't need to know their secrets to success or anything.
Subscribe to your YouTube channel.
Oh yeah, true.
These are smart students. These are smart students. I always said that. Yeah. So what's the plan now for the rest of the day?
To come back.
I'm going back with during the afternoon.
You're going back
Yeah, to UK.
to the UK this afternoon. Okay. And you too?
I went to Cork this afternoon.
You're going to Cork this afternoon, and then you're in Dublin, so
I'm going home.
you're going home this afternoon. Yeah. Well, it's good to see you guys then. And will you be around for much longer, or are you going soon?
I think it's all.
Yeah, because maybe they have questions, but they're too shy to ask you with me around. You know, they might be like, that Stephen guy, is he any good now? Be honest with me, you know. So they might want to ask you after class, maybe. So will you be around Emer's office, or yeah? Yeah. Well, look, if you see these guys around and you want to ask them questions, you can. Yeah.
I thought Andrew also be here next.
I haven't seen Andrew for months. He might be around later today.
No, next week.
He'll be
Next week.
Yeah, actually we'll
Okay.
be coming.
For the award, like the highest score in engineering or something.
Oh, for you.
Andrew.
Yeah.
Wow, that's really.
Yeah, I'll double check that before next week. Okay. Yeah. Okay, guys. So it's good to see you.
Yeah.
And just keep an eye out if you want to ask them questions. That's okay. Yeah. Having a good time at university. Yeah. Happy memories of DIFC.
Of course.
Yeah, I miss that too.
Yes. Okay, I'll see you around later, guys. Okay, it's good to see you.
Yeah.
Don't cause much trouble.
Yeah.
Okay. Right. So that's good. Let's see. We just finished that one, so that was a hard one then. I think now you could probably practice some of the questions. Can I just see this workbook here? Let's see now. Yeah, good. So for about 10 minutes, I have 5 questions here. If you work really hard, you might get them all done now in 10 minutes, and then you have no homework. But whatever you don't finish, if you can finish them for homework, then draw beautiful graphs for me, please. Okay, beautiful graphs.
In here?
No, in your copybook. Let's see, I need this one up here. Yeah.